Day 12, we're going to talk about continuously compounding interest and something called APert. Common logs. As mentioned before, the common log has a base of 10. The common log is used to measure acidity, pH scales, sound in decibels, and earthquakes, the Richter scale. Each earthquake level is 10 times stronger than the level before it on the Richter scale. So what that means is if there is an earthquake that is level 1 on the Richter scale versus level 2, a level 2 earthquake is 10 times stronger than a level 1. A level 3 is 10 times stronger than a level 2 and 100 times stronger than a level 1 because 10 times 10 is 100. So again, as we increase in level, each one is 10 times stronger. Which means by the time that you get to level 10, which is extremely rare, happens almost about every 1,000 years, see how much more powerful it is. And this doesn't even show a level 10 magnitude. So here's level 1. Actually, that's a negative 1. Here's level 1. Here's level 8. So you can see how it grows exponentially because, again, each one is 10 times stronger than the one before it. So whenever a log is written without a base, it is base 10. So when you see example 1 right here, rewrite in exponential form. Log of x equals 4. It's log base 10 of x equals 4. And then to change it to exponential form, you would do 10 to the power of 4 equals x. So there's changing it to exponential form. Again, start with the base and loop it around. And if we were to solve for that, we would get, what is 10 to the 4th? 10,000 equals x if you're solving. You know how credit cards compound interest monthly? Can you write the equation for monthly compound interest? So in the last lesson, we looked at if you want the amount, you take the starting value, and the amount that you owe increases if you don't pay it off, so 1 plus. And if it's monthly, it's your rate as a decimal divided by 12 months per year. But then it's the number of years, t, times 12, or I could write, I guess, 12t. So however many times per year times the number of year. In reality, many things are not compounded at a specific time. An example is population. Babies are not just born at the end of every month. We say that population increases continuously. A bacteria population may double every 4 hours, but it is increasing throughout those 4 hours, not suddenly doubling in value when exactly 4 hours have passed. Let's see how the formula is calculated for continuous interest. Let's say you start with $1 and compound it 10,000 times for 1 year at 100% interest. Let's write that equation and solve that number. So we're going to take our starting value, $1, and we're going to compound it at 100% interest, so 100% as a decimal is 1. You're going to do it for 10,000 times a year for 1 year. So we can type that in and let's see what we get. So I'm going to pop up my scientific Desmos calculator. And we have let's clear it all. So we'll start with 1, and it's increasing at 100%, so 1 divided by 10,000 times a year. To the power of 10,000 times for 1 year. I guess I don't need that times 1, but if I did, it would be, it's not going to let me do it. I wonder how I would do it. Oh yeah, times 1. Let me do it. I guess it doesn't like that. Okay. All right, well, 10,000 times 1 is 10,000. So there it is. It's this number, 2.718145927. So I'm going to write that down. It's about 2.7181. 2.7181. All right, well, what happens if you take that same dollar at 100% interest and compound it 1,000,000 times a year? What do we get? Okay, so what I'm going to do is in my calculator, I'll write the equation here. So 1 plus, it's going to be the same equation except instead of 10,000, I'm going to put 1,000,000 in place of that. And it's 1 time a year, so times 1,000,000. All right, so let's type that in and see what happens. So I'm just going to add in a few more zeros. All right, so There's 1,000,000, 6 zeros, and okay, look at what happened to the number. It's essentially the same, 2.7182, if I round to 3. 2.7183 if I round it. Oh, I guess I didn't even write that forth. Okay, so you can see essentially the numbers are the same. This number that you're seeing isn't a special irrational number like pi. Irrational in that it doesn't have a fraction to represent it. You can't, there's no pattern to it, no repetition. It is called E for Euler's number, and he's the one who discovered it. And if we type this into our calculator, e to the first power, we're going to get that number. So 2.7181, and it keeps going like pi. Let's see if we can find that on scientific decimals. Is there an E here? Oh, here it is. So I'm going to clear all. I'm just going to type in E, and there it is, 2.7182. That is a number like pi, but it's E, or Euler's number. And we're going to use that when something's continuously being compounded. We saw when we did it 1,000 or 10,000 versus 1,000,000, like this number stayed relatively constant. And so that is built into our formula instead of doing 1 over 1 divided by blah, 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 blah. So instead of doing this part right here, we have this E in our formula. So whenever you see a problem that's growing exponentially and it's being continuously compounded, you're going to use this formula, A equals PE to the RT, instead of the one that we looked at when it's compounded a certain number of times per year. So continuously we'll use this, and we're just going to go over some examples of how you use this formula. A lot of things stand for the same thing as before. A is still the amount at a certain time, P is still the starting value, R is your rate as a decimal, but in APert you don't add or subtract the 1 for this rate. T is still time, and now we have this new number E, which is programmed in the calculator. And what you need to know is the log base E is ln. So whenever, instead of log base E, we're going to use ln to solve. So we'll do some examples with that. Okay, so first, how do you solve something with an E? And again, this is log base E of 16 equals x. And then in that box it says, hey, if it's log base E, that's the same as ln. So we're just going to say ln of 16 equals x. So if you have an exponent with E as the base, when you log it, it's actually the natural log. So we'll say ln of 16. Let's type that in. Again, it should be here as one of our functions. Oh, there it is. Oh, let me delete this. All right, so ln of 16, and the answer is 2.77258, blah, blah, blah. So about 2.77 all round. So x is about 2.77. And what that means is in our calculator, if we were to type in e to the 2.77 power, we get really close to 16. So it's solving for that exponent. All right, let's try another one. So this time we have 4e to the 2x equals 22, and we're going to solve it the same way we've been doing other stuff. We want to get the base by itself. So first step, divide by 4. So e to the 2x equals, ooh, this is some fraction. That's 5.5. We're going to log it. So the step I'm going to write in black, you don't have to write. So it's log base e of 5.5 equals 2x. But log base e is the same as ln. So really we could have just written ln of 5.5. So whenever you see the e here and you log it, it's ln. So ln of 5.5 equals 2x. And then the last step is we'll divide both sides by 2 to get x. So in my calculator, I'm going to type in, let me clear it, ln, so that's under function, and then 5.5, so I go to main and 5.5, and then close my parenthesis, and then I'll divide it by 2, and then we get our answer, which is 0.85237. So here, x equals 0.23857, I'll put 0.23. All right, and you can check your answer by if you plug it in, you should get about 22 when you solve it. Okay, let's do some word problems with this new APert formula. It says assume $100 is deposited into a savings account at 6% interest, compounded continuously. So again, whenever you see compounded continuously, you're going to use APert. When will the money be double the original amount? Okay, so we want the amount to be 200. equals 100. And it's A equals PE to the RT. So we put the E here. The rate is 6% as a decimal. We don't add or subtract 1, so 0.06. And then we need time here. So here we're solving for T. All right, let's solve. First step, divide each side by 100. So we get 2 equals E times 0.06t. We're going to log it. Remember, when you log E, it's ln. So ln of 2 equals 0.06t. And to get rid of the 0.06, we're just going to divide by 0.06. So in my calculator, I'll type in ln of 2 divided by 0.06. Okay, so ln of 2 divided by 0.06, and we get about 11.55 years, around that's 11.6 years. So after 11.6 years, our money will double if it's growing continuously at 6%. All right, number 4, Najma invested $1,000 into a certificate of deposit. You might have heard the term CD as an investment. It stands for certificate of deposit 3 years ago. The CD is now worth $1,270. Assuming the interest was compounded continuously, what was the interest rate? So you see continuous, you think APert. Let's plug in what we know. We know the final amount is $1,270. We know the starting value was 1,000. We don't know the interest rate, but we know the time was 3 years ago, so 3 times R. All right, once you plug in, we're going to divide as the first step to get the E by itself, the base by itself. Okay, so we get 1.270 equals E to the 3R. We're going to log it, log both sides, and if you log base E, it's ln. So ln of 1.27 equals 3R, and then we divide each side by 3, and then we can type that into our calculator. All right, so let's do that. Okay, clear all. ln. So ln of, forgot it already, 1.27 divided by 3. Was it divided by, yeah, it was divided by 3. All right, so the rate, the interest rate was growing at about 8%, 7.96%, about 8%. Okay, I can write 7.96%. Okay, so again, this is the rate as a decimal, so we could change it to a percent by moving the decimal place over twice. Okay, Danny plans to invest $500 at 8.25% interest compounded continuously. How long will it take for his money to triple? All right, so if we triple 500, we get 1,500. It's growing continuously, so E to the, we know the rate, 0.0825. We don't know time, so T. All right, first step, divide by 500. So we get 3 equals E to the 0.0825t. We're going to ln it, natural log it, so ln of 3, oopsies, equals 0.0825t. To get t by itself, we will divide. So divide each side by 0.0825 t. Oh, not t, I'm sorry, we leave t on that side. Okay, so then you type it in. I'll just do my calculator here. So ln of 3 divided by 0.0825, and we get, let me pick purple, t equals about 13.3 years. Okay, so that long to take for Danny to take his money to triple. If he could find an interest rate at 8.25% compounded continuously, you can triple your money in 13.3 years. Okay, and then last problem, and then we're going to review. So bacteria is growing continuously from 40 bacteria to 326 in 120 minutes. Find R if T is in minutes. Okay, so we're ending up with 326. We start with 40. It's growing continuously. For 120 minutes, we need the rate. So we plug everything in. First step, divide. All right, 326 divided by 40 is 8.15 equals e to the 120r. We're going to log it, but again, it's going to be natural log because it's base e. So we're going to say ln of 8.15 equals 120r. And then last step, divide by 120, and then you can type it in. So in your calculator, you'll do ln of 8.15 divided by 120. Get your rate. I'm just going to type it in. And I get about 0.017, or it's growing at a rate of 1.7%. Okay. So to summarize, we've looked at a lot of different formulas this chapter. It's essentially the same formula, just little things change. So if it's annual interest or once a year, your amount equals your starting value times 1 plus r to the n power. If it's any more than once a year, you have to divide your rate by the number of times per year, but then multiply the number of years by that as well. So multiply, divide by n, multiply by n. And if it's continuous, it's a equals pe to the rt. So we can take a look at how that will change in each equation if we look at annually, quarterly, monthly, continuously with the same amount. So let's start with $1,000. How much will you have after 5 years at 4%? And we're going to do it with all these equations. So annually, just once a year. So we'll have 1,000, and it's growing at 4% a year for 5 years. So if I type that in, okay, here's how much you would have if this was the case, $1,216.65. All right, what if it was compounded quarterly or 4 times a year? What would that look like? So you would have 1,000. Sorry, my finger keeps hitting the thing. 1 plus, oh, okay, but we're doing it 4 times a year. So 0.04 divided by 4. And then 4 times a year for 5 years, so 4 times 5. All right, so if we type that in, I'll show you on this calculator. Oops, clear. All right, so 1,000 we start with. 1 plus, and it's 4% divided by 4 times a year. And then to the power of 4 times 5 years, so 20 times, and we get 1,220.19. 1220.19. Okay, so you can see it does increase by like $4 if we go to quarterly versus annually. Okay, how about monthly? So the only thing that's going to change is the number of times we divide it per year. So 0.04 divided by 12, and then it will be 12 times 5. All right, so I'll type that in. Okay, and I get 1220.99, almost 1221, I guess, if I round up because it's 9965. So I'll round up to about 1,221. So monthly is $1 more than quarterly, less than $1 more. And then continuously, what if you just kept calculating the interest and kept doing it right after it was done continuously? So A equals PE to the RT. Your rate is 4%. The time is 5 years. So if we type that in, so 1,000, we need to find the E to the power of your rate was 4% times 5 years. And you can see that it's like 40 cents more, so 1221.40. Okay. So just a review of all the different formulas and how they work, we can see that it does level off after some amount. Your assignment is the day 12 daily practice, but skip 6 and 7 because we have already done them, unless you want to do them again. But otherwise finish, I think it's 44 and 45. Oh, and 46. Okay, so number 8 on 46, do that, but then you can skip like the last 2. So about 3 pages. Oh, skip 9 and 10. Skip 9 and 10. We'll take that. All right, that is it.